Just before we begin, here are some tables that you'll need. Shows you the surface fracture and versus tensile strength table, and then some of this. So the question we're going to solve is plot on the log coordinates estimated SN curves for A, bending, B, axial, and C, torsional loading of a 1-inch diameter steel bar having an SU of 110 KSI, SY of 77 KSI, and machine surface for each of the three types of loading. What is the fatigue strength corresponding to 1, 10 to the 6 or more cycles, and 2, 6 times 10 to the 4. So first given, we have 1-inch diameter steel bar, SU 110 KSI, SY 77 KSI, and we also know that it is machined surface. So for the required, what is required? We have A, bending load, B, axial load, and C, torsional load. Also required to find the strength at 1, 10 to the 6 or more cycles, as well as we're supposed to find the strength at, or stress strength, I should say, at 6 times 10 to the 4 cycles. So we also have to have or make some assumptions. So for this, we'll be pretty conservative. Look at our assumptions here for CG and CT mainly. So let's assume that our average reliability is 50%, which gives us a CR of 1.1. And our test is conducted at room temperature, which means a CT of 1. So let's get to solving A, the bending load. So if you look, we're given the, first endurance limit is equal to SN, and so that's what we have to solve for. And we also have to solve for the safety factor, which is SF. We're given these formulas, SN equals SN prime times CL times CG times CS times CT times CR. We're also given the safety factor, SF is equal to 0.9 SU times CT. You can see that's given right here. So let's do these calculations. So SN prime is equal to 0.5 times SU, and this is for steel, which is what we're dealing with today. And SN prime, therefore, is equal to 0.5 times our SU, 110 KSI. SN prime is equal to 55 KSI. CL, we determined, is equal to 1. And you can see here, Y, for bending, that is 1. Our CG is equal to 0.9. That is because if you look here, CG, and we have a 1-inch diameter pipe, so less than 2 inches, which will give us, not there, but a bending CG of 0.9. Next, our CS is equal to 0.75, because if you look at the graph here, it's 110 KSI right here, and we have machined surface, we know that, we go up and over, and our CS is 0.75, just about. Our CT, we know from our assumptions, is equal to 1, and our CR, finally, is equal to 1 as well. So now for the calculation, SN is equal to 55 KSI times, we'll have 1 times 0.9 times 0.75 times 1 times 1. SN is therefore equal to 37.13 KSI. Now we must calculate SF, which is equal to 0.9 SU CT, which is equal to 0.9 times 110 KSI times 1. This gives us a value of SF is equal to 99 KSI. Now let's go over to our SN curve. We have peak alternating stress, which is S log, or also SF, versus life cycles, N. SF here equal to 99, so our safety factor. And we know the other point on this graph will be at 37.13 KSI. And that's at 10 to the 6. So that's where we plot that point. And as soon as that reaches that point, we draw the line across. So next, we'll look at axial loads. Axial loads, SF is equal to 0.75 SU times CT, and our SN prime stays the same. So our CL is equal to 1 in this instance. CG, we look over, we're going to take a average, which is 0.8, or also known as conservative. Our CS, again, is 0.75. Our CT is 1, and our CR will be 1 again. Now, let's calculate for SN for axial loading. We have 55 KSI times 1 times 0.8 in this instance, times 0.75 times 1 times 1. Our SN is therefore equal to 33 KSI. And our SF is equal to 0.75 times SU times CT, which is equal to 0.75 times 110 times 1. That'll give us a value of 82.5 KSI. Go back over to our graph. We're going to plot these points. SF is equal to 82.5 for axial loading, and SN is equal to 33 KSI. Just draw this line, go over, and that's what that line looks like. Now let's solve for torsional loading. So in torsional loading, we have SF is equal to 0.9 SUS CT. So we can deduce that S10 to the 3 is equal to 0.9 SUS, which is roughly equal to 0.72 SU. Therefore, SF is equal to 0.72 SU CT, which gives us a value of SF that is equal to 79.2 KSI. Our SN prime stays the same at 55 KSI. CL is 0.58, as you can see there. Our CG is equal to, let's look over, 0.9. 0.9 CS is equal to, once again, 0.75. Our CT is equal to 1, and our CR is equal to 1. Therefore, SN is equal to 55 KSI times 0.58 times 0.9 times 0.75 times 1 times 1. Our SN is therefore equal to 21.53 KSI, rounded. Now let's go over to our graph, plot that, SF at 79.2, and our SN at 21.53. Join those points together, and we have our torsional SN line. Once again, this is bending, this is our axial loading, and this is our torsional loading on the SN curve. So now we must solve for one fatigue strength at 10 to the 6 or more cycles. For that, we just plot in these numbers that we've calculated before, because if you look at the life cycles, they're plotted on 10 to the 6. So there's our numbers. And 2, fatigue strength at 6 times 10 to the 4 cycles. So how do we do this? Start at 10 to the 4 on the life cycles, jump 1, 2, 3, 4, 5, 6, and we'll go up from that point, which is 6 times 10 to the 4 life cycles, or life n cycles. So for the bending, we're going to start, let's change this to roughly because it's an estimate. So this is how we're going to estimate at 6 times 10 to the 4. So it looks like it's roughly 73 KSI. The next one, we go up from that point. I'm going to say it's roughly 55 KSI for axial loading. And lastly, torsional loading. We'll go up to that point, go over, and it looks like 45 KSI. Thank you all for joining me today, and I'll see you next time.